conversation from John about structures and symmetry, and Ruthie went over Miller indices. What I want to do is try to put those together in a better understanding of the morphology of crystals, because both elements are involved in describing the morphology. I want to make a couple of comments first, but mostly what I want to do is draw crystals and talk about them using a crystal drawing program. Might take a little bit different tack on some of the things that have been said, but I think we can say that Miller indices define the orientations of planes in space relative to some axial system. The planes themselves are theoretically infinite in extent, and they're located some distance from the origin that we use to define them. But because we can remove common multiples and things like that, we're really talking in a sense about a family of parallel planes rather than just a single plane. And it's some measure of a distance from the origin that defines what specific plane we're talking about. As I just sort of implied, the Miller indices are always defined in relationship to the unit cell or the lattice. So they can be different depending on what crystal system you're in and depending on the shape of the unit cell within the system that you're dealing with. But ultimately, they reflect the symmetry of the crystal structure. I don't know if I can I guess I can't get rid of this thing that says I'm talking. I don't know if anybody else sees it or not. But so geometrically speaking, a crystal is bounded by portions of planes, which we call faces. If you have two planes in space and they are not parallel to each other, they intersect to form a line, which is potentially a crystal edge. Three planes that are not coplanar define a corner and three lines, and four planes would define a completely enclosed space, which we could potentially call a crystal. So that the shapes of faces are determined by the surrounding faces and where they intersect that part of the plane that we call a face. Crystals must totally enclose space. I'd like to facetiously say that if they don't, all the crystal juice drains out and they just shrivel up. That's not really what happens, but crystals are, by definition, an object that encloses space totally. And crystals are, by definition, always convex. So there's no grooves, no dimples. All the edges point outward. All the corners point outward. You will find a duality in the way people talk about things. Crystallographers tend to talk as if the symmetry generates the crystal. And they'll say, well, we've got a plane over here. We rotate it 90 degrees. That creates another plane. Rotated another 90 degrees. It creates another plane, and so forth. And from a geometrical perspective, that may be perfectly adequate. But clearly, mineral crystals grow from a very small beginning as a nucleus by adding successive layers of atoms. And they do so in a way which is consistent with the attractive forces in the crystal structure, and the symmetry emerges from the atomic arrangement. So it's really more a question of the crystal defining the symmetry rather than the symmetry defining the crystal. And having said that, I'm going to have to bounce out of this for a minute because I got to turn on my crystal drawing program, and it puts a lot of stress on my computer, so I don't like to leave it on. Old computer overheats pretty easily, so let's go back. So here we are, starting up an emulation of the old operating system. And we'll start crystal drawing program. And I'm going to start talking about the isometric system, the full symmetry part of the isometric system. And I'm going to start with a familiar set of Miller indices. What's going on here? Here we go. 100. You've seen that several times, so you probably know what to expect it to look like. So when we hit the button to compute, well, we got more than 100. I'll put on the Miller indices. And turn on the axes. We got 1, 0, 0, but we also got the 0, 1, 0 and 0, 0, 1 that Ruthie talked about. What we have here is the form that's defined by the symmetry elements from the plane 1, 0, 0. Or you could start from plane 0, 0, 1 or 0, 1, 0. You always get the same result. This is a crystal form rather than a crystal face. Each it's composed of 6 crystal faces. You can perhaps consider what's going to show up when I get over and look at this back side of the crystal here, 0 bar 1 0, or similarly the bottom here, 0 0 bar 1. I want to go now to a different set of Miller indices, which are also familiar, but there's perhaps more instructive. I'm going to change this to 1 1 1 1. I can type right. And 1 1 1 is in this system is the octahedron. It's composed of 8 equivalent faces, each one of which is an equilateral triangle, and it reflects the threefold symmetry that John referred to as being the defining factor of the isometric system. You get it like this, you can see the threefold symmetry pretty clearly in both crystal faces and their arrangements to each other and in the crystal axes. Go back to this. But so this is for the maximum symmetry class of the isometric system. If I go to something different, sometimes it gets a little cranky. I'm going to go to a different system. I'm going to go to the system, the symmetry class that is characteristic of sphalerite and tetrahedrite, and use the same Miller indices. And what do we get? We get a totally different form. Instead of an octahedron, we have a tetrahedron. The faces are still triangles, but they're oriented totally different. There's only 4 of them. And this reflects the control or the influence, the interplay between the Miller indices and the specific crystal class within the isometric system. If we go beyond that and look at the tetragonal system, as John commented, the tetragonal system is not constrained to have the dimensions along the z-axis or the c dimension equal to the a dimension. So I'm going to change this, make it a little different, make it say 1.7. And you can maybe think what you expect to see now. We're back to having 8 faces, but they're no longer equilateral triangles, they're isosceles triangles. It's as if the octahedron got stretched in a vertical direction to produce the form we have here. And that reflects the fact that the c dimension is longer. So it's still the same intercepts, but because the dimensions...
Hey, Pete, we got a question. So
right.
What is a crystal class? From Jeff Kruger.
Okay, without spending a half an hour, a crystal class is a subdivision of a crystal system. Each crystal system has several classes which have different details of their symmetry within the defining factor that John mentioned. For example, the isometric system having 4 threefold axes. So different numbers of mirror planes, different numbers of subordinate axes, and so forth. And it's something that takes too long to explain in detail. But so for the tetragonal system we're talking about now with the maximum symmetry, we have a tall octahedron, if you will, really a bipyramid. We can change that parameter again, and if we make this say 0.8, make it shorter than the A direction, we get a crystal that looks more like a zircon. This is still all 1, 1, 1, the form 1, 1, 1, but in a different system. To take it further, we can look at the hexagonal system. And now we're going to find that we have a hexagonal bipyramid. instead of 8 faces, we have 12. And this is where Ruthie's comments about the fourth, well, the additional index, the I index, show up. The program doesn't show them, but the face in front is 1, 1, bar 2, 1. And the face over here is 2, 1, bar 1, bar 1. If you only have the 3 indices, it looks like they might be totally different kinds of faces because they have different numbers. But if we have all 4 numbers, it's clear that they really belong to the same form. Again.
One more quick one. Is this a program available for Windows as well?
Well, this particular program is obsolete. It's my favorite one, but there is a version of Shape for Windows. It can be ordered from shapesoftware.com. I will tell you about a couple of other programs at the end that you may want to consider for this kind of thing too. I'm going to do one final example here. And I'm going to do it a little differently. I want to look at the Triclinic system. No, let's see. I'm going to choose the one that's called bar 1, but it doesn't really matter. This is the one that has an inversion center. Can have 3 different values for the 3 different axes, so I'm just going to invent some numbers here. Make this one 9.2 for the heck of it. 120, 187. Now, if I can tell you from experience that if I just put in 111 and tell it to go, I'm going to have trouble. It's not going to be a complete crystal. The crystal juice is going to melt out and it'll stop my program. So I'm going to put in the basic ones first, 1, 0, 0. And I have to put each one in for each axis because they're not equivalent to each other. With that, I get at least a crystal. It encloses space, but you can see it's like a squash box. It's not, faces are not perpendicular to each other. But then put in the 111. There's the 111, and you see it really is composed of only 2 faces which are parallel to each other. By itself, it doesn't define a crystal because it leaves the rest of the space open. So what this is really all showing, I guess I could show one more thing here, is that the shape of the crystal depends not only on the various forms that are present, but how big they are relative to each other. So I can push 111 way in close toward the center. There. How do we get? All right, there we go. And I now have a crystal which is getting really tabular. Should look a little bit like an axonite crystal. The only difference is the relative size of the different faces. So as long as you only have one form, you have somewhat limitation, but most crystals have more than one form, and the relative sizes of the different forms is an important part of controlling the crystal morphology. There are some other things I could do, but I think in the interest of time, I will stop this part of it and go back to the PowerPoint for a couple of final comments. So what we really see is that the morphology, the shape of a crystal reflects, first of all, the symmetry system and class to which the mineral it belongs. It also reflects the shape of the unit cell and the lattice within that symmetry system and class. And then finally, it reflects the forms that are present and their relative sizes. And this is where the Miller indices, which are tied to the first 2 items, serve to quantify the shape of the crystal. And finally, we have to recognize that we're drawing ideal crystals. Regular crystals have asymmetries of growth, which are due to things going on in the environment and so forth. And so often real crystals deviate from the ideal form these first three elements define. And if that's a lot of words to finish up, maybe this is a simpler way to look at it. The crystal morphology is basically an interaction between the structure and the symmetry that's inherent in the crystal and the various aspects of the environment. So that basically concludes what I wanted to say, but I just wanted to point out, if you're interested in exploring this yourself, SMORPH is a program which is used to do all the drawings on MinDat of crystals. It's available at this website. You don't actually download it, you use it there, but you can choose any of a number of minerals, or you can put in your own parameters for to define the crystals. You can do all kinds of modifications of shapes and forms and twist it around and do essentially all the things I did and more. And it's all free. Another one I want to mention is called Euhedra. It's available at the MSA website, and it does somewhat of a different class of things. But one of the things that it does really neatly is to calculate the passage of light through a transparent crystal. So it actually shows you with a fair degree of accuracy the back sides as seen through the front of the crystal as you move the crystal around. Two different programs that do a lot of the same things.